Hello everyone, and welcome back. I decided to make this video to try to clear up some doubts and respond to all these frequently asked questions which I've been getting lately. So at least I can condense them in a video and try to also delve a little bit in the depth of this spot welding phenomena, let's call it like this. Also, if you are here for the first time, please check out my playlist where I analyze all the other spot welders. There are a few, and while you're at it, if you feel free to subscribe and like if you like the content, which always helps the YouTube algorithm. So at least it's more popular. These videos are starting to trend, I see, and I get a lot of questions. Even if I've actually replied to most of them in the videos, I see it's kind of dispersive, as you have to go through maybe more videos to try to find what you're looking for. So I try to condense them here and let's say have this video as a reference for all the questions and methodology and other things related, let's say not just let's say connected to the defects, which most of the other videos are, but the whole procedure. So I made this document where, as you can see, there are these frequently asked questions, and just starting from the first, usual questions I get is which battery can I use? Can I use a car battery? What are the characteristics? The cold cranking amps? What's the dimension? Can I use also a 4S LiPo pack? Or what's the maximum voltage I can use? Now, all of these are very similar. Basically, the default configuration would be a 12 volt power source, so that's a standard AGM battery. 45 ampere hour is, if it's new, it's fine. If you have a larger battery and it's let's say also, like say not brand new, but has maybe a couple of years on it or whatever, even over 60 ampere hour, you can also use it. It really depends on the state of the battery. Of course, to spot weld you need current, so the battery has to be in working order. It has to be, let's say, performing well. And so if you have a used battery lying around which is sulfated, no, that won't do it. Better have a new battery. So yeah, 3S LiPo packs, 5,000 milliamp per hour minimum, and at least 50 Cs. So regarding these questions, you should look for 3S, 5,000 milliamp per hour, and 50 C at least, plus. A 4S can do, so it's actually also acceptable, but you're really pushing the limits because some circuits, especially the older ones, older versions, are trimmed in the, let's say, 13 to 14 and a half, 15 volt range. 16 volt is already going a little bit over, and that may let's say create some biasing problems, especially with the initial models that use this the 3 transistor configuration with the push-pull. Now, if you don't know what I'm talking about, check out my one of the first earlier videos where I analyzed one of the first models which had these problems where you had to modify some resistors to get the bias properly. So let's say ballpark range 3S, 5,000 milliamp per hour, 50 C. If you have 65 or whatever, or 90, even if peak, you can use it. Or a 12 volt AGM 45 ampere hour battery. And if you have more, again, you can use it as long as you start calibrating your welds with a very low millisecond setting. So you can start from even 2 milliseconds just to check. This, of course, is connected to the whole system. Now, we will talk about this later. So, based on these, let's say, replies here, I can highlight them. This is the general ballpark figure. If you have, there are people who are using 4S with other more, let's say, more recent spot welders without problems. You can do that. But you're also introducing additional internal resistance. So why have an additional, let's say, pack, which it's true, it increases your voltage, but you also have some other milliamps in series. So if you have a 3S 50C plus pack, it's really more than fine. And you're stressing the batteries less. So keep this in mind. Of course, if somebody already has a pack and doesn't want to buy one, okay, consider that these packs can be stressed, and they tend to inflate, blow up after a couple of years, because it's the technology, it's not a long-lasting technology. So forget having packs that you can keep for 5 or 6 years without problems. These are, their performance will drop very quickly. And here I replied also to, is higher voltage better, let's say, for welds? That's exactly what I was talking about. It's the internal resistance of the battery. So if you have one extra cell and you go to 4S, then you have some 8 to 9 milliohms more. And yes, it's true that you have 4 volts more, or 3.6 under load. But yeah, it will probably increase the current slightly, but it will also stress a lot more everything else. So I wouldn't say this is true. You should stick to the 3S value, which is the let's say calibrated value voltage for these packs. Okay, so higher voltage is not always better. Now, power supply. You really can't use a standard power supply, even switching power supply, even if you have a very capable one that can deliver, I don't know, maybe 60 amps at 12 volts. You need a peak current of at least over 250 amps at least, and peak currents actually exceed the 400 amps. So even with a very capable, let's say, power supply, you wouldn't be able to spot weld. You would need a very big beast, and that's why industrial equipment use transformers with a very thick winding, so that the secondary, so that the voltage is low and the current is very high, capable of 10,000 amps and more. So this is the, let's say, industrial welding of thicker strips and then even car chassis. So yeah, you can reach even up to 20,000 amps. So even, you have an idea of the power involved. In this case, we are talking about very small devices, so you just need a decent peak current and a let's say capable power unit, which is very easily achievable with a battery pack, but hardly achievable with a standard power supply. You would need to probably stack a few power supplies in parallel to get that kind of performance. There are some let's say powerful server switching power supplies which can deliver a kilowatt each as on power, and that's around 24 volts. So you could stack about 4 of them, and you would probably be able to get spot weld. But yeah, then you'd have to have 4 power supplies stacked in parallel, and then you'd need to somehow limit the current, because 24 volts is way too much. And okay, I digress, but it has been done. Then I get the question about a separate power supply. I mean, the spot welder is powered separately, respect to the battery. Now, this is possible, but if you have the correctly modded and decoupled logic, you do not really need this, because these spot welders, we are welding once every few seconds. So there is really no need to have a constant power source. Properly decoupled logic is fine. You just need a 470 microfarad or 1000 microfarad electrolytic cap on the MCU, not just to power the MCU, but to trigger the FETs, which require also a decent amount of impulse current, and that was explained. The gates do that. So that's that. Then another question: can I weld thicker than 0.15, 0.20, 0.25, or even 0.30? With these kinds of mini spot welders, they are calibrated, let's say, for maximum 0.15 millimeters. Going to 0.20 is already an overkill, and going to 0.30 is practically impossible if you don't want to destroy it very quickly, because you're reaching currents which, let's say, are not calibrated for the array of FETs that are arranged in that way. You start reaching, let's say, the limit of the design of the semiconductor design in this case. I will talk about all of this a little bit, why about this later, and it involves stacking, parallel stacking the FETs, and FETs are not all the same. They are mass produced. They have to be matched, and this is very important, because even a small difference of impedance of resistance between one drain source and the other, it will overstress one FET, which is overperforming the others, and that's the FET that will blow up. So it doesn't. That's why, for example, the purple mini spot welder, which has the possibility to add more FETs on the back, is not really a let's say great idea, especially if you do it in two instances. You would have to replace all of the FETs. You would have to remove the ones that are on, buy a tube of FETs which are carefully matched, and then mount them. Else you're probably using half of those FETs, or maybe you're lucky enough within 8 FETs you have 4 or 5 that are matched. Because really, to get that kind of spot weld, you really just need 3 FETs, but they have to be perfectly matched, and that's not the case. So they put more. You have 5. I mean, maybe they get, you're lucky and they're better matched, and so you have maybe 3 matched. Maybe you have 4, which are actually doing all the work, and 1 is actually not doing anything. So it's a little bit difficult to, let's say, spot it in the beginning, or get this concept. But it's like having an array of Christmas lights. And once upon a time, the Christmas lights were filament type. And what happened if one Christmas light blew? Well, you would have to replace it with the same exact model, with the same exact power, because it means it has the same exact resistance. Otherwise, if you put a slightly larger, let's say higher voltage rated one, you would think, well, the others would suffer. No, the higher voltage rated one would suffer, because it has a less resistance, and it would be the one that would be dissipating more heat, because the other ones would be, say, harder to push, to light, and so you would be blowing up that one. Especially with a 220 volt or whatever, let's say balanced series is what it's called. That's why it's called balanced. They all have to be exactly the same, and that's why maybe you would notice one light up slightly more than the other one, and that light would be the first light that would die. So yeah, it's kind of the same thing with FETs. They are all arranged in parallel, but they have to be exactly, let's say, have exactly the same internal resistance to be performing the same way. And it's very hard to do that in mass production. You can do that, but it's very hard to do that between different batches. So that's why. and that's what is FET matching. So when you buy a bunch of FETs and they're all the same, and you go to the reseller site, DigiKey, RS Components, or Mauser, or whatever, they will state these FETs are matched, they are batch matched, and so you're paying also for that, not just for FET, but you're paying for the matching warranty. So when you need to replace a bunch of parallel FETs like these, you always need to replace them in a batch. If they're in push-pull configuration or in other kinds of configuration where they work individually with others, it's a little bit different. It's a little bit more condoning, even if it's stressful still, but it's working alone. And here, it's handling all of the power because it's individually. Here, they are handling it in parallel, so they really have to work as a team all together. They really have to be like siblings and identical. Now we have reached the transient voltage peaks, or the surge. This is something that I didn't talk about a lot initially. Mentioned it somewhere. Some spot welders had them. The TVS diodes, for example, the first initial one. Many people ask me, what are these black large things on the bottom? And that's what they are. They are transient voltage suppressors. It's simply a kind of diode, because it is a diode, which intervenes when there is an over voltage, which can destroy the FET because of the, let's say, reverse peak, or it's exceeding the drain source or the gate source, or the gate voltage. So what it does is it clamps this voltage. It starts conducting after a certain voltage. It's practically a zener. But it's not exactly, it doesn't have exactly the same characteristics. It performs as a zener, but it has some slight differences, so that it can handle the very intense peak, because it's a very brief moment. While zeners, standard zeners, are usually handling a biased current constantly, the TVS handles a very powerful peak current for a very brief amount of time. So they're constructed slightly differently. So you want to protect a reverse volt transient of 15 volts, you would put in a 15 volt TVS. And that's what they are there for. And they are very close to the FETs, because they have to be very close to the source, to the, let's say, junction they need to protect. One last frequently asked question is if I can modify, or if it's possible to modify the purple mini spot welder for an external trigger. Yes, it is. I actually didn't talk about it because I've seen, I think, some video of a mod. It's pretty easy. I think I mentioned it. You just need to cut a trace, and the trace is the voltage detect, meaning the terminal detect. And then once you've cut it, you solder the part that goes to the MCU to an external jack, and the other side of the jack is connected to the positive. So when you close that switch, it will emulate contact, and it will trigger. Of course, then when you're triggering by hand, it won't work anymore. Automatically using the contacts. Here it is. Okay, you see this track here? It should be in the center. Yes, I will zoom it up a little bit. So, okay, so this track, under this written the output minus, it goes in the middle here, because this is a separate track. It reaches the top, and here, exactly where this via is, it goes to the MCU. It goes to the detect pin of the MCU. So you can interrupt this track wherever you want. You can cut it here, or even cut it here. And once you've cut this track, then the automatic detection will no longer work, and you will need to scrape, like I did here. You would need to scrape. So this is the buzzer, by the way. So it was disturbing me, so I interrupted it. Just scrape some of the silk screen off and solder there your let's say little wire, and you can possibly put a jack here or something, a mini jack, and one side of the let's say the side that goes to the MCU goes to one side of the jack, the other side of the jack goes to the plus, so you can solder it or take it from here, scrape a little bit from here, and this is the other side. And that will take care of the, let's say, manual trigger. If you want to, let's say, put it back to automatic, you will just have to disconnect the wire and just, you know, resolder the trace here. You can even get one of those jacks that has an automatic interrupter where you insert a jack, it opens up a contact. So it opens up the contact that goes here, and then it just leads it to the other side, which goes to the positive. That should be possible. So that's this purple mod manual trigger modification. Okay, so now I want to talk about the resistance spot welding basics, because what we're doing here is resistance spot welding. And this is something that is of course industrially used, and it works like this. The weld that is created, it's due to the temperature reaching the fusion point of the contact material. So the temperature rises, and this rise is induced by this enormous current that is flowing through this small area, and a relatively small resistance due to the contact between the two surfaces. This dissipates this energy into heat, which is called Q, and this reaction is the Joule heating law, and this is the formula: Q equals to I squared times R times T, and the I is the current, so it's the square of the current times the relatively small resistance times the time. That's the total energy, heating energy. In this process we have losses, which are due to resistances of the cable. I call them parasitical or unacceptable because they heat up the cables, they heat up the FETs, they heat up the tracks and the electrodes and the same battery, which we really wouldn't want. In an ideal world we wouldn't have them. And all this gives you a combined loss resistance of R, so let's say some milliohms. Then we have the acceptable loss, which is the only resistance, the sole resistance of the spot weld. And this is needed because we need that resistance for the Joule heating law to take place for the weld. Now, the current that we use has to be proportional to several parameters, which is material thickness, the material we're welding, the type of the material, the pressure we're applying between the contacts, and the total contact surface, which then creates the nugget. It's the so-called nugget, which is the weld, the spot weld. So the thicker the material, the larger the contact surface, and the more contact force is required, and current, if you want to scale out. This is the concept. Now I did a graph. I took this from a website when I integrated some data. And here on the left you can see the sheet thickness. Now this kind of thickness is very large. As you can see, this is industrial spot welding. We're talking about 3 millimeters, and I added the smaller 0.3 here. It starts from about 0.63. So as you can see, the combined thickness starts from 1.2 millimeters. This is the force that is applied. By the way, it's kilonewtons, so it's around 200 kilograms of force. And this is the welding current, and you have 8,500 amps. It's a lot. And the industrial welding works with cycles. These cycles are based on the mains frequency. So you get a 6 pulses for a total of 120 milliseconds. And then there is the hold time, which is the delay between each pulse, and that is 1 cycle. And this is for 0.63 millimeters, which in total is 1.26. And you can see here on the right the current rises pretty linearly, and the thickness is rising also pretty linearly. But if you go here to the weld time, you can see that there is a difference in rise time here, because that is when things change. This is when they do 3 complete cycles, separate cycles, with 4 cycles of weld times. So they repeat this process 3 times 7, that would be 21, but they don't do it 21 cycles, they do it in sets of 3 plus 2 at the end. So that's why the this curve, this weld time changes. It has to be increased a lot, and this is because if they would have done just 21 cycles, they would have started fusing and melting the material completely out. It would spatter out, and it would not be a decent weld. You would perforate the material. So you can reach a certain limit of weld time before you perforate the material, and you will have to stop welding, let it cool down, and continue welding later. And they do this by doing it 3 times, 3 sets of 7 cycles plus 2 end cycles. And you can see that the total weld time jumps 100 milliseconds more because of all these intermediates, and you would have also 4 cycles of hold between. So it's pretty long. It's pretty long. And all of the welds after these 2 millimeter thickness, so you have 2 sheets of 2 millimeters, are like this. As you can see, they go up linearly, but they go up much more steeply, because a lot of energy is lost by, let's say, dissipating the heat, because it's necessary to drop the temperature. So this is a technique that industrial welding, spot welding, uses to avoid melting the let's say the 2 layers. Otherwise you will get a hole and the spot weld won't hold. It's a perforated one. And a similar thing happens with batteries. You have to be careful, because single spot welds can also perforate batteries. Now, what we were talking about here in the, let's say, in industrial spot welding, this is called, let's say, double-sided spot welding, or what I call pinch spot welding. You have 2 electrodes which pinch each other. I can show you. Okay, this is a spot weld. This is seam welds that are very close to each other. This is the tips, and here is the pinch spot welding. As you can see, it's a cycle, and here is the force, and then there is the current. Of course, you apply first the force, then you apply the current, or the whole cycle, and the weld starts forming in between the 2 materials, because that's the path where the resistance is actually highest. So you have a flat surface here to have a good contact, and then in the middle you start getting, also because of the heat and the insulation, you start getting the fusion point, and then you stop welding, and that's the weld, that's the fused material. And on the top here you can see a nugget. You get this nugget here. It's like this round area where you've soldered, where it's fused, and it's behind, it's in between the 2 surfaces. When we're spot welding batteries, we're not doing it double-sided, we're doing it single-sided. So this means that both contacts are on the same surface, and this means that it's slightly different, because you have also an additional path between the 2 electrodes. So you have one contact, and beside it you have a second contact, and usually there are a few millimeters, usually 4 or 5 millimeters between each contact, and you are using the, let's say, the container of the battery, or the top of the battery, as the other side, but there is nothing supporting it. So this is a single cell. You have the contact here, then you have one electrode here, which have, let's say, of course, 2 resistances, and then you have this path between the 2 weld points, which is another resistance. It's very low, but it's there. So it's not so efficient as double-sided spot welding. It's not so efficient as pinch welding. And so you need probably a little bit more voltage just to overcome these slight losses. But for batteries, it's fine. And so the nugget that's formed has to be here and here. And as I showed before, it's very dependent on the surface of the electrode. That's where electrode shaping comes in. Now, just a word here about the nickel strips. Here, you shouldn't really use a nickel strip thicker than 0.25 millimeters, because the battery's wall thickness itself is 0.3. It's 3 millimeters thick. Here it is. Cell housing goes from 0.22 to 0.28. This is the wall thickness, and the base is around 0.3 millimeters. And it's also similar to the 21700, the newer, larger lithium-ion cells. If you use a 4680, then okay, it handles more current and it's thicker. But usually people are spot welding 18650s, and this is the limit of the base, and also relatively of the top, though the top is less critical because it's not in direct contact. The top is actually detached from the battery, so from the battery's case. It has a protection which is used to protect the battery from exploding. And there is a small, let's say, description here. This is a positive terminal, then you have the insulation ring, then you have this so-called burst disc. Then you have another insulation spacer and the current interrupt device. This is for overcurrent protection, and this is for overpressure protection. And both of these are necessary for commercial batteries, because otherwise you risk really getting a danger or fire hazard or explosion. So this opens up in a controlled manner, and it will leak the pressure out. You can hear like a little noise. And this instead just interrupts the battery. It has a little filament, and once the overcurrent is reached, it just opens up, and the battery is in fact, it's called current interrupt device. It's a tab. And that's it. The battery is actually, the cell may be still okay, but it will be dead. You will try to test it, it will be dead. So that's the that's this little wire here. So yeah, it's a protection mechanism. Also, additionally, the amount of pressure put on the weld point is important. You shouldn't overpressure it or underpressure it. You should have the contact that should be there should be enough to, let's say, block the strip in place, and not allow it to move around when you move the electrodes. Okay, that's the more or less a ballpark kind of like contact force. If you manage to move the electrodes and they slip around, or the contact below slips around, that's not enough. You need to press slightly more. All right, before switching to the electrode shape, another word about these metal strips. People want to put very, let's say, thick metal strips on batteries, when, as you see, it's not really necessary, because each battery can hold usually up to 7.5. If you get a standard lithium-ion, standard lithium-ion cells still market around 2,500 milliamp per hour. 3,000 are exceptional. If you see anything more, it's all bull. It's fake. Panasonic, Samsung, Sony, official values are, industrial values, and let's say acceptable and tested values are 2,500 milliamps, derated from 2,750. So they start out at 2,750 and they reach 2,500 during time. That's how professional or serious manufacturers work. If you see a single cell where it's written, I don't know, 5,000 milliampere hour, no, that's not possible. Not at least in 18650, of course. I'm talking about 18650s, these kind of this dimension cell. And this kind of cell can go up to 5C constant, maybe up to 10C peak currents for brief amounts, so a few milliseconds. But constant is usually 5C if it's a good cell. So if you do 5 times 2.5, there you get it. You get about 12.5 amps. But generally speaking, that's why it's in the middle here. Generally speaking, these cells can usually go up to 3C. Okay, the ones that 3, 4. You have to find some very, very good manufacturers which will give you 5C constant. So we're talking about this power range for every cell, and it's usually peaked. But if it's constant, it's, let's say it's stick around 10 amps. 10 amps on a 0.15 millimeter strip is fine, and you can simply spot weld it instead of 4. You can put 6 spot welds if you're really worried about it, because all the current flows, of course, through the spot weld. The rest of the surface, it has to be in very tight contact to really conduct any current. So usually it's where the spot welds are, and that's why industrially spot welded batteries have a slightly larger surface contact, and because they are calibrated better. And instead, when you use these mini spot welders, usually it's smaller. So for me, if you have a 0.2 millimeter strip, that's more than enough. 0.50 millimeter strips are fine. If you really have some doubts, you can also double strip them. You can solder a bottom strip and solder a top strip on top, using different positions where you spot weld, so they are spot welded to each other. The current will still pass through the first spot welds, but it will be distributed along the two tabs, along the two strips, which is also good for reducing the overall load on, and also losses on each strip. But really, this is for very high intense current use, large packs, and plus they are usually 4S, 5S, 6S. So you have a lot of these batteries in parallel, which then from one tab are put in series with another. Now that single tab, that has to handle the current, so that's the tab that you should parallel. Anyhow, the most, let's say, the others are, it's a whole parallel thing. The end of the tab that connects to the other battery, the other pack, that should be put in series. So you can maybe do multiple strips. Now back to the electrode shape. The electrode shape, these are electrodes from one kind of kit, and these are electrodes from another, which I have actually rounded off. Now, what happens when you put one of these electrodes at an angle? You will only get a weld in this small area here. So you have an extremely small surface contact area. This in diameter is about 1.5 millimeters. Here you get, I don't know, less than a tenth of a millimeter or slightly more. So it's natural that if you have one of these contacts, one of these, let's say, probes, and you are at an angle, you will be welding and perforating much easier the surface of any tab. And now what happens is that this corner will start filling in, it will start, let's say, depressing, going into the surface, and you will notice that it will kind of stick. And that's because of the extremely high temperature reached. Now that's, I mean, I would say it can be okay, but the overall strength of the weld is inferior than to that of a surface area like this. This is smaller than that electrode, because this is about 1 millimeter, or let's say 1.2 millimeters. But the surface area here is certainly less than a millimeter, but as you can see, the depression, this curve, when you press it down, it will fuse and reach this area here. So when you weld with this kind of electrode, it might seem that the electrode surface is smaller. In reality, it's bigger, and you're getting a proper nugget, because this part here will kind of sink into the surface when it's heating up, and all of this will be in contact. So you have to press, not exceedingly, because you need to leave a little bit of let's say resistance so that it will heat up, and while it's welding, the pressure, it will make it sink in. And if you don't hold the electrode exactly flat or at an angle, you will still have a curvature. You can see that you have two curvatures here, and these will also sink in and create this kind of nugget here. So it's important and better to have this shape rather than the shape that you saw before, rather than this one. And if you do find an electrode like this, just round it off. Try to round it off, or make a point here, not a very sharp point, kind of a flat point like the other one, and you'll see that it will start to be harder to spot weld, and you will have to increase in current slightly, and thus the time, but the welds that you will be getting will be certainly more stable. You can see here by the light reflection the difference in surface. If you just consider this corner of this disc here, it's nothing. If you try to put this flat, you probably won't be able to get any weld. This is way too large for the spot welds. You need to round it off like this. So these are two kinds of terminals. I don't remember. I think this is the classic mini spot welder one, because I have a few, and this was given with another, maybe the purple spot welder, and it's kind of random. They pick what they have. The lengths of the cables are the same. So I would suggest this kind of surface. As you can see, the terminals are basically the same length. Cables are the same gauge. Contacts here are crimped here they're crimped slightly closer. So yeah, maybe, but this is copper, so it doesn't really make a big difference. These electrodes here, actually they sell them separately. If you want to change them, you can let's say pull them out and crimp them back in if you're able to, but they should last quite a long time. You really need to weld several hundreds to get them. This was the other picture that I took to check the bottom. So that's the discussion related, that's the argument related to the contact points shape, the electrode shapes. Now, a word on how the spot welder basically works. Now that we've let's say spoken about all of the aspects. Basically, you have a battery pack where it's 3 cells or 6 in series, where it's a AGM, lead acid, or a LiPo. By the way, these are only 2 cells. They didn't have the drawing for the 3 ones, but it doesn't matter. So you have this, then you have your spot welder, which is just a switch. It's an electronic switch, a semiconductor switch, which is timed by a electronic timer, and then you have your electrodes, and here you have your weld. So this is what happens. So it's an extremely simple thing, but rather complex to understand everything that happens, especially during an electronic switch. And the reason I drew this analogy here, this is the same circuit above and below, is because the below circuit represents the resistive total of the circuit. So you have the battery, which has an internal resistance of R1, the 2 wires, which have 2 resistances, which is R2 and R3. You have the terminal and the other wire, which has another resistance, and you have the FETs, which has another total resistance, which is R5, and the weld itself, which is R6. So And then you have something that is called transient voltage surge, because all of this creates a very, even if small, this does have a slight inductance and it can create this surge. So all of this adds up to all of these resistances, and this is the total resistance of your circuit. R6 is in green because it's the only resistance loss we really want, which is exactly on the weld. But however, in the real world, we have all these losses, which are the cables, the semiconductors, and the wires, and the battery itself. So this is a very ugly graph I drew, but it's the only quick way to just try to explain what happens when you lower these resistances too much and your electronic semiconductor is not capable or is not designed to handle these transient voltage peaks. Now, if we have a certain amount of resistance, here in blue, you will have an initial very high current, which can be 400, 500, 800 amps, and these will drop down pretty rapidly because the battery is unable to sustain that. But the weld is so brief that in these 20 milliseconds or so, it's okay. Let's say it's tolerable by the battery, and then the weld ends. Now, if you decrease these resistances, you will have a much higher peak because the battery's voltage is basically the same. It hasn't been changed. The battery's internal resistance hasn't been changed. What you have changed here is you have shortened the terminals, and you have shortened the terminals here. So this initial very high peak can go over a limit, and this limit can be even over 1000 amps. It can be even 1500 amps. It's very brief, but if you reach that limit, that red line, all those individual FETs you have here, if they are not matched, they will fail. One of them will immediately fail. That's how you destroy the FETs. On the other hand, you can destroy them when you end the weld, because while they're turning off, this transient peak, this transient surge disturbs, and this is a field effect. It goes and destroys MOS, that bridge, and it will short out the FET, and that's it. So while this is happening, you still have the electrodes on the weld, so the circuit is still closed. So it will go like this. You will turn on, it will weld, and when it will stop welding, it will short out the FET, and that will blow a hole in your battery. That's how it actually happens. So whether it's shorting out in the beginning or shorting out in the end, you won't really notice it. It's very quick. It's too fast for you to notice. So this is why it's kind of important to keep a certain amount of wire, which is the cables that they have delivered. Some FETs, for example, the purple spot welder, can be powered directly on the PCB with a XT60 connector, with a female XT60 connector. But then you have the LiPo pack, which has some leads. So that's also substituting for the leads that you would use for a 12-volt AGM battery, right? And then again, if you have extra long leads, that's not good. For example, when you have a LiPo pack and then you have a female connector connected and then another wire leading to the spot welder, that can probably be shortened by 50%. But I wouldn't exceed that, shortening that length. Always keep the cables at their length because they already heat up enough, and that just demonstrates the amount of current and losses they go through. If you don't exceed with the let's say battery peak current and keep the cables at a decent level, these spot welders actually can go through a lot of abuse. But you can be unlucky and have areas of FETs which aren't really matched, and one of them will blow up. That's why there are also all these controversial let's say experiences with these devices, because many people find them fine, and other people use them 2 or 3 times and then they just blow up. Apart from the fact that they need these mods, which I talk about, the major reason is the fact that the gates are not, let's say, saturated correctly, and that makes them work in an area which is really not, they have a very high internal resistance, and that's when they blow up. Before they start conducting, all this current wants to go through, they overheat. Yeah, so that's one fail. The other fail is the transient voltages, and the other fail again is the overcurrent. So these are all the aspects to consider. I hope this kind of clears, this analogy kind of clears up what it's actually all about. When you want to exceed certain, let's say, spot welding energies, you have to go to electromechanical stuff. You can't really use FETs anymore. You could use them, but it's an overkill. You just need mechanical stuff. Also because the times involved are much longer, as you've seen from this table here. You are not talking about 60 milliseconds. We're talking about at least 200 milliseconds, and with 10 cycle times and 2 hold times in between. So you can do this mechanically, and any timer can handle this, these kind of timings. Instead, handling the sub 10-20 millisecond timings like is needed for these batteries, that's more electronic. That's more electronic control, and there you need a FET, so it's more justifiable. But then again, industrial applications calibrate it for the batteries, and they do the spot welds also using mains, and it's very precise also. It can be risky if you don't know what you're doing and you're handling one of these enormous devices here that have these kind of electrodes. This kind of machine, if you're not careful, it can blow any material up. It will spatter all over the place and makes holes in your clothes if you are not careful and not wearing protective wear. And just as a comparison, as you can see, all of these electrodes, these are the electrode ends, they are all slightly flat. This is important. There has to be a slight flat area. Of course, it must be proportional to the weld type. So if you scale this down to our electrode, you can see that the one I showed you is in fact the same proportion. And you have these round beads because they will create a slight depression. Depending on the kind of the material, if it's softer or harder or whatever, you will choose one of these electrodes. And this electrode here, which you see it doesn't depress so much. This one does, but it's kind of like at 45 angles. This one is rounded, so you can actually spot weld not precisely at a 90-degree angle. This one has a little flat surface, so it supposedly does have to be done at a 90-degree angle, but if not, it can still handle certain asperities. So it all depends on what kind of material, the thickness and everything that you need to handle. Okay, so that should be it for the frequently asked questions. I hope that this has explained the basic concepts, and if you're interested in this document, I can upload it somewhere and link it, so it's just for reference. Maybe I will be adding something to it, or I'll just add it to the description somewhere. Okay, so hope you enjoyed and liked this content. If you are interested, just please subscribe if you don't want to miss out any future videos, and if you haven't yet seen, please check the playlist, which I will link at the end, which has all of the spot welding related videos about all the mods, and of course other discussions on more detailed effects of the semiconductors, the FETs especially, how to properly drive them and overcome the Miller effect and other related mods. So see you next time.